Hi, I'm Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
And today we're going to be continuing our discussion of AP Physics 1, Unit 1, with a quick little talk on how to graph position versus time. So here we just have our two little lovely axes, our position on our y-axis and our y-axis, and our time on our x-axis. And so we're just going to work through a little example of graphing the motion of someone, in particular my cat, because she is perfect and I love her, as she moves throughout the backyard in this example. So here we're going to say that Juniper, my cat, who, just for all of you visual learners, Juniper is a very small black cat with little tiny white mittens and a bow tie. So that doesn't help you at all in physics, but I feel like it's helpful for like your edification as a human person. So there we go. So Juniper's position at time 0, she's going to start exactly at the back door, or at 0 meters. So we're going to represent this. Our time is at 0 seconds right now, and her position is 0 meters. And then we're going to say she sees a bird, and so she starts running across the backyard. And in 2 seconds, she travels 4 meters. So we're going to move over here to 2 seconds on the x-axis, up to 4 meters on the y-axis, and we're just going to put a little dot right there to say, hey, 2 seconds have passed and she's moved 4 meters. Not so bad. Right, but then we're going to say that the bird sees her, so she freezes in some vain attempt to become invisible, because that's what she does. So over the next 2 seconds, so now we're moving up from 2 to 4 seconds, she doesn't move. She stays at the same position. So since her position is unchanged, she hasn't moved at all, she's still at 4 meters. So we're going to put a little dot right there. Or those are a little low. Let me adjust them up just a tad. There we go, that's a little better. Okay, then over the next 1 second, she makes a mad dash towards the bird, sprinting almost as fast as she can. So from 4 to 5 seconds, she's going to move 6 meters farther away towards the bird. So from 4 to 5 seconds, so we're moving upwards here to 5 seconds, she moves 6 meters farther away, which puts her at a total distance of 10 meters away. Her position is 10 meters from the back door, right? And then, in the last second, the bird has flown away, it's gotten away, she hears me calling at the back door, and she sprints all the way back to the back door. So that means in 1 more second, going between 5 to 6 seconds, she sprints all the way back to the back door, which we denote as having a position of 0. All right, so now, just like any time whenever we plot a bunch of points on a graph, if we want to graph them, we just connect them with little straight lines. So we're just going to do that real quick. So from 0 to 2 seconds, she moves from 0 to 4 meters. Then from 2 to 4 seconds, she stays flat at 4 meters. Then from 4 to 5 seconds, she goes up to 10 meters. And then from 5 to 6 seconds, she comes back and sprints all the way back to the door, back to 0 meters. Now, an interesting thing to note about this graph is, well, do you remember when we calculated slope back in algebra? Slope is just, the formula that your math teachers would always say is rise over run, right? Like from the y equals mx plus b kind of stuff. So if slope is rise over run, well, if on this graph we're talking about rise over run, that means your change in your y-axis over your change in your x-axis, right? So our change in our y-axis here would be our change in position. So, and how do we denote change in position, right? It's a displacement, and the variable for that is change in x, which I know this is confusing because our position is on our y-axis, not our x-axis, but just know this x here, I'm talking about position. I'm talking about displacement, I'm not talking about my x-axis, okay? And then, well, what about our change on our y-axis, our run, in other words, on rise over run? Well, that's our change in time, in seconds here, right? So we have our change in position divided by our change in time. Well, that's a formula that we've seen before, isn't it? In fact, we talked about it just a video or two ago. Our change in position and change in time, that's the same as our velocity, right? Or in other words, we calculate that out by saying our final position minus our initial position divided by our final time minus our initial time, right? So in other words, if rise over run gives us a change in position over a change in time, the slope that we have on this graph, that's just our velocity. So you can really easily calculate the velocity of Juniper as she's running around the backyard just by calculating the slope of the different parts of this graph. So let's do that. Let's run through a little bit of practice. Let's calculate first, and here, I'll write this out again, so don't worry. Let's calculate our slope of this first section here from 0 to 2 seconds. So we said that our velocity is the same as our slope, which is equal to our change in position, or delta x. And again, this x means displacement, not x-axis, over our change in time, right? And in fact, I might even just change this to y, just to be a little more clear. Our change in position on the y-axis, or no, that's confusing to do, we'll stick with x, over our change in time. Or in other words, our final position minus our initial position. X final minus x initial over our final time minus our initial time. So, well, what is that in this instance? Well, our final position here at 2 seconds is 4 meters. So that would be 4 meters minus our initial position. Well, Juniper started at the back door at 0, right? So that's just 4 meters minus 0 meters over our change in time. 2 seconds minus 0 seconds. That gives us 4 meters. Wow, that's not how you write a 2. That was a t. 2 seconds minus 0 seconds. So we have 4 meters and 2 seconds. So that would be 4 meters divided by 2 seconds, which is equal to 2 meters per second. And there we go. That's our velocity over this first little bit. Let me write that right here, 2 meters per second. Now let's do this next bit where between 2 to 4 seconds, when the bird has seen Juniper and she is frozen. So 2 to 4 seconds. So over this section, what's our velocity is equal to our final position, which is 4 meters. Nope, that's not at all how you read a graph. Our final position at 4 seconds, which is 4 meters, minus our initial position at 2 seconds, which is still 4 meters. Then in our denominator, we have our change in time, right? So that's 4 seconds minus 2 seconds. So 4 seconds minus 2 seconds. Hey, but hey, here in our numerator, we have 4 meters minus 4 meters. That's 0 meters, which makes sense. She doesn't move at all. She's frozen, trying to be invisible for the bird. And then in our denominator, we have 4 seconds minus 2 seconds, so that's 2 seconds. So that means our velocity is 0 meters divided by 2 seconds, or 0 meters per second. In other words, here, when we have this horizontal line in our position time graph, Juniper is at rest, or at 0 meters per second. She's not moving. She starts at 4 meters per second, at 4 meters at 2 seconds, and she ends at 4 meters. Her position doesn't change at all. So now a lot of the time when students see a graph like this, they have this initial instinct of saying, okay, so I start at the bottom of the hill, and then I move uphill, and then I'm moving across a flat surface, then I start going uphill again, and then I start going downhill. But that's not what this is at all. Well, a graph is a graphical representation of your information here, of your position over time. This x-axis is your time, not any kind of position. And your position here on your y-axis, that's not your height. That's just how far away you are from your origin, how far away you are from where you started. So here, when we have a horizontal line in our position time graph, that doesn't mean we're walking across a flat surface. That means we're staying at the same position while time is continuing to pass here, which means we're at rest. If you can get this, then you're going to be just fine in everything with graphing position time. A horizontal line means you're staying at rest. Your position is unchanging. Now that we have that, let's go and calculate just these last couple velocities, and then we'll be pretty much good on graphing position. So let's do here from 4 to 5 seconds. Our velocity is equal to our change in position over our change in time. It's our rise over our run. We end at 10 meters, and we started here at 4 meters. And the time that passed from 4 to 5 seconds is 5 seconds minus 4 seconds, which is equal to 10 meters minus 4 meters, which is 6 meters in our numerator, divided by 5 seconds minus 4 seconds, so that's just 1 second. So our velocity over this last bit, when Juniper is making that mad dash towards the bird, is 6 meters per second. All right, now let's do this last segment here. So this is 6 meters per second. All right, so now let's calculate this last section from 5 to 6 seconds. So our velocity is equal to our change in position over our change in time. So our final position minus our initial position over our final time minus our initial time, which is equal to, well, our final position here is 0 meters, right? Where Juniper's back at the back door. But her initial position over this little time segment was 10 meters. So we have 0 meters minus 10 meters. Then our final time minus our initial time. Our final time is 6 seconds, and our initial time over this segment is 5 seconds. So that's equal to, well, 0 meters minus 10 meters is negative 10 meters. 6 seconds minus 5 seconds is 1 second. So we have negative 10 meters in 1 second, or negative 10 meters per second. As Juniper is running backwards in the opposite direction she's been traveling this whole time, back towards the back door. So her velocity here is negative 10 meters per second. Is it entirely realistic for a cat to move at 10 meters per second? Maybe not for ordinary cats, but we're just going to say that Juniper is very fast in this example, okay? All right, now that is almost all of what you need to know for graphing motion. We have talking about how our slope is our velocity, and if you ever forget that, just think about units, okay? That's always a good key of where to look in physics. If you ever don't know what's going on, check out your units, and oftentimes the clue you're looking for is hidden right there. Our change in position, meters, over a change in seconds, change in time, or seconds, we have meters divided by seconds and rise over run. That means your slope has units of meters per second, which means it's a velocity. If you have a flat line, you have a velocity of 0, you're at rest. Your velocity is, your position is unchanging, which means your velocity is 0. If you have a downward sloping line, that doesn't mean you're traveling downhill. It means you are traveling backwards, back towards your origin. In this case, that means you have a negative velocity. All right, everyone, thank you so much for sticking with me through all of that. Y'all are troopers. I hope you have a great day and happy physicsing.